Yeah, so my name is Katona. I'm from the University of York, and I'm going to be presenting this work, which was done in collaboration with University of Coimbra, with Penousal and others. And I'm going to talk about indirect encoding and why I think they are important and they are really interesting and have really interesting properties, but why in practice they don't seem to work very well, and how we can improve that. So what is indirect encoding? In case of direct encoding, we have a one-to-one mapping between learned parameters and the natural representation. For example, in case of a neural network, we have a separate learned parameter for each of the weight of the neural network. We can do some kind of transformation between the parameter space and the natural representation. For example, we can do simple transformation like coordinate transforms. For example, transforming the parameters from polar coordinates to Cartesian coordinates. But I would still consider this direct encoding because there aren't any complex interaction between the parameters. So in case of indirect encoding, there are some kind of complex interaction between the parameters when you transform them, so that they have some interesting properties, which I will talk about in the next slide. So an example of such a method is Hypernetwork, where the weights of a neural network are generated with a pattern-producing network. So each weight is queried by another network. So what are the properties of indirect encoding? So the first one is that it allows for controlling the exploration during learning. So the way this is possible is that this transformation between the learned parameters and the natural representation allows evolution to turn random genotypic variation into any distribution of phenotypic variation. So this is similar to how generative adversarial network can turn random variation or random noise into any distribution, for example, phases. And why this is important is because it allows evolution to control exploration in a similar way, like, for example, CMA-ES, which uses a covariance matrix to define a Gaussian distribution to explore in the next generation. But this covariance matrix is calculated using some rules which were designed by the creator of the algorithm. But when we use indirect encoding, we can evolution can come up with interesting or efficient exploration strategies automatically. So another interesting property of indirect encoding is that it allows for reusing the parameters multiple times to build regular and modular structures. This property was demonstrated really well by the paper Convolution by Evolution, where they used the evolved the weights of a fully connected network. And evolution was, when they used indirect encoding, evolution was able to discover convolution from scratch. So indirect encoding can allow us to automatically learn efficient structures like convolution and efficient exploration strategies like CMA-ES in a data-driven way. And the reason why this is important is summarized really well by Richard Sutton in his essay, The Bitter Lesson, where he talks about the observation that throughout the history of machine learning, researchers always try to build in some extra knowledge in their agents, which increased performance for a while, but eventually their general methods like learning and search always surpasses performance. So indirect encoding allows us to discover efficient structures and strategies in a data-driven way in the spirit of Sutton's argument. But the problem is that in practice, indirect encoding doesn't seem to work really well. So to answer the question why this is the case, I would like to try to answer the question, a simpler question first. Why do self-adaptive algorithms doesn't work very well? And this question was answered by a paper by Kluhn et al., where they let evolution adapt the mutation rate, and they observed that if the fitness landscape is not smooth, evolution fails completely to set the mutation rate. And the reason is that evolution tries to avoid deleterious mutations. And so it trades off the ability to adapt in the long term for short-term benefits. So in case of indirect encoding, this problem is much more severe because we are not only learning a mutation rate, but we are learning a whole distribution of offsprings. So these trade-offs between short-term benefits and long-term adaptability is much more severe. So a short-sighted algorithm is not able to make advantage of the capabilities of indirect encoding. And what's more, it's much more likely to make things worse, since there are much more bad exploration strategies than good ones. So the solution to this problem is to optimize directly for adaptability or evolvability. And we only recently have the capability to do this efficiently with algorithms such as evolvability ES, which is an evolutionary algorithm which directly optimizes for evolvability, and model-agnostic MetaLearning, which is a gradient-based method which optimizes for the ability to adapt. So in order to test whether our theory is correct that indirect encoding doesn't work because we are using short-sighted algorithms, and it would work much better if we would use algorithms where we select for the ability to adapt, we run some experiments with where we trained neural networks for image classification. We had the greedy algorithm as gradient descent, and we used the fashion MNIST dataset. And for the algorithm which optimizes for adaptability, we used model-agnostic MetaLearning on the Omniglot dataset. And we compared direct encoding and indirect encoding. And for indirect encoding, we used hypernetworks, which is a technique to indirectly encode neural networks by projecting the weights from an embedding space. And we found that in case of the greedy algorithm, direct encoding worked better. But in case of the MetaLearning, which selects for the ability to adapt, indirect encoding worked better, which support our theory. But the effect is not very large, so it would be nice in the future to test this in other domains with other indirect encoding, other algorithms. Yeah, thank you for your attention, and I hope to see you in the poster session.
Okay, Adam, thanks for the presentation. I guess this finished this session.